And our speaker today is José Calcines from Universidad de La Laguna, who is going to speak about topological complexity using arbitrary covers. Take it away, Jose.
Okay, so I share. Okay, can you see it?
Yes, make it full screen.
Okay.
Perfect.
Okay, perfect. So thank you very much and hello everyone. First of all, I would like to thank the organizers of this seminar, Dan, John, Jesus, for inviting me to give this talk about my recent research on topological complexity. This talk is based on a paper, a note on covers defining relative and sectional categories, which was published 2 years ago. In that paper, it is studied the sectional category and the relative category by using covers that where its members are arbitrary sets. And whenever we are dealing with absolute neighborhood retracts, they are the same as the classical ones. So I will try to explain the basics of that paper in this talk. So I have divided my presentation into 3 different sections. The first one, I will give a brief introduction to Srinivasan's result on generalized Lustenist-Niemann category. The second one, I will explain the main notion of the paper, which is the generalized sectional category, which is a kind of a generalization of the Srinivasan's notion. And I will give the main results and consequences. I will have to talk a little bit about absolute neighborhood retracts. Finally, I will deal with the relative case where the monoidal topological complexity is involved. And there is this notion of the relative category. I would say relative sectional category in the sense of Doeruene-El Haouari. So let's begin. Okay, I think everybody here knows the notion of topological complexity. For a space X, this is the smallest n such that the X cross X admits a cover by n+1 open subsets, on each of which the B evaluation vibration admits a local section. That is, we have here strictly commutative triangles. These sections are called local rules or local motion planning algorithms. Observe that here I am using the normalized version. That is, for me, the topological complexity is 0 if only if the space is contractible. Okay, as we know, this is a numerical homotopy invariant, which is nice for homotopy theory. There is this Lustenist-Niemann category, which is a classical numerical homotopy invariant, where it is used also open covers by elements that are contractible within X. But in these 2 papers by Tulsi Srinivasan, she's a former student of Dranishnikov, these 2 papers in 2013 and 2014, she introduced the notion of generalized LS category of a space in order to study the LS category of piano continua and general metric spaces. This is the smallest integer n, such that the space admits a cover by n plus 1 subsets, not necessarily open, which are contractible within X. So this is a homotopy invariant. Of course, this is a lower bound of the category of X. And surprisingly, this is an amazing result for me, that for absolute neighborhood retracts, it agrees with the category of X. So cat X is the cat G of X whenever we're dealing with absolute neighborhood retracts. So this is the starting point of this work. So we wonder whether there exists an extension of Srinivason's result to topological complexity, and something similar for monoidal topological complexity. So in order to deal with this, to face this problem, I will consider a sectional category, which is a more general invariant that extends the topological complexity and the category, and also the relative category in the sense of Doeruene-El Haouari for the case of monoidal topological complexity. Okay, so you know what the sectional category is of a fibration. This is the smallest n, such that the base of the fibration admits a cover by n plus 1 open subsets, on each of which there exists a local section. And if we consider local sections up to homotopy, this notion can be easily extended to any map. And of course, as I said, it generalizes the notions of topological complexity and the category of the space. This is the sectional category of the B evaluation fibration or the diagonal map. And the category in this case is the sectional category of the path fibration or the map from the singleton to X whenever we have a path connected space. Okay, so if we consider the generalized version of the sectional category, that is, we adopt this notion by just considering arbitrary sets, we obtain the notion of generalized sectional category of P. So we have a cover of P by arbitrary sets, and each of which there exists a local section, and the least cardinal of this cover is the generalized sectional category of P. Of course, this is a lower bound of the sectional category, and again, taking local homotopy section, this notion can be easily extended to any map. This is a homotopy invariant in the following sense. If we have two maps, F and F prime, which are connected by two homotopy equivalencies, forming a homotopy commutative square like this, then their generalized sectional categories are the same. For a proof, one just has to consider a repetition of the proof given in the classical case. This is the first example, important example, the generalized category of X when X is path connected. This is, of course, the generalized sectional category of the path fibration or the map from the singleton to X. This is an expected result if we have a map where the codomain of the map is path connected and base, then the generalized sectional category of F is a lower bound of the generalized category of Y. And when X is contractible, we obtain the equality. This is because we have here a homotopy commutative triangle, showing that if we have a local homotopy section of the map going from the singleton to Y, then we obtain another local homotopy section with respect to F, composing with the map from the singleton to X. So this is quite similar. This is to mimic, in fact, the proof given in the classical case. This is the most important example for me in this work, the generalized topological complexity. This is just consider the generalized sectional category of B evaluation fibration or of the diagonal map. By the properties of the secat G, we have that this is a homotopy invariant, and when X is path connected is between cat G of X and cat G of X cross X. Now I want to establish or to see the main result of the work, which is for any fibration between absolute neighborhood retracts, the sectional category of the generalized sectional category agree. So I need some facts about absolute neighborhood retracts that I need to recall. So recall that an ANR is a metrizable space satisfying this condition. For any map F from a closed subset of a metrizable space to Y, one can find an extension of F from an open neighborhood U of A in X. So this was introduced by Borsuk the past century, in the early 30s. And it's a notion that is widely spread in algebraic topology. As examples, we have the Euclidean neighborhood retracts. These are examples: topological manifolds, Banach manifolds, locally finite CW complexes. A CW complex need not to be ANR, because in general they are not metrizable. But what we know is that any CW complex has the homotopy type of absolute neighborhood retract. In fact, we have this nice result. Space X has the homotopy type of a CW complex if and only if it has the homotopy type of an ANR. I need, in order to prove the main result, I need to present two crucial results on ANRs. This is the first of them. If we have a metric absolute neighborhood retract, then one can find a function epsilon from B to the positive numbers, such that any two maps Fg from any space, any metric space to B, that are epsilon close are homotopic. And by epsilon close, I mean this property: for any point Z in Z, there exists another point in B for which these two images, via F and G, belongs to this ball centered at P and with radius epsilon B. So they are controlled by this function. They are epsilon close. So for a proof of this result, one can find, for example, in this book, but Theory of Retracts by Hu, and it is not very difficult to check. Perhaps the most important result is this one. This proposition, the modified Walsh lemma, which states the following: consider any map F from a subspace A of a metric space, and to K, where K is a metric ANR. If we have this, then for any function, epsilon, from K to the positive numbers, one can find an open neighborhood of A in X and a map from that open neighborhood to K, such that it is an extension of F, act to homotopy, and it verifies this condition for any element in U. There is another element in AU, satisfying that these two distances are some kind of controlled by epsilon. This epsilon of FAU and epsilon FAU, the distance between JU and FAU, and the distance between U and AU. Okay, I have to say that this result was proven by Srinivasan in the last paper of hers, but the statement is a little bit different. The second condition, it only appears the first condition. The distance between JU and FAU is less than the epsilon FAU. But if one goes deeply into the proof of that result, one realizes that in fact the distance, this other distance, the distance between U and AU, can be made as small as necessary. So we can also consider that we have this other inequality. Okay, so this is more or less the two crucial results that we need in order to prove our main result. So this is the result. We have a vibration between ANRs. Then the sectional category of P is the generalized sectional category of P. That is, the sectional category can be given by arbitrary sectional subsets that cover the base space. So before going to the proof, I need three main ingredients. This is the first one. Consider for the first crucial result, we can take a function, epsilon, satisfying that any pair of epsilon closed maps to B are homotopic. So we have this epsilon. The second ingredient is this one. We use the continuity of P, and we use the epsilon. So for any E, we can take epsilon PE. And from this number, we can pick delta of E, satisfying this continuity condition, as usual. So in fact, this delta depends on the epsilon, okay? And the third ingredient is the construction of this function in E. This is the minimum, epsilon bar of E is the minimum between delta and epsilon P. So now we are prepared for the proof of the result. So we have just to prove this inequality because the other inequality is obvious. So we start with any subset of P having a strict local section, S. That is, we have here a strictly commutative triangle. So what I want to do is to enlarge A with an open neighborhood and to extend S to S prime in such a way that the composite with P is homotopy to the corresponding inclusion. If we achieve this, then we're done. So we apply the modified Walsh lemma to this map, to S, from A to E, and epsilon bar. So the modified Walsh lemma then tell us that we have another map, S prime, from an open neighborhood of A to E, satisfying that is an extension up to homotopy of S, and it also satisfies this nice condition. For any U, one can find an element in A satisfying that these two distances, the distance S prime U and SAU, and the distance between U and AU, are controlled or are less than epsilon bar SAU. So now one has just to check that the composite of P with S prime is homotopic to the inclusion. But by construction, it suffices to check that these two maps are epsilon close. So the composite of S prime with P and the inclusion are epsilon close, and then by the conditions, we have that they have to be homotopic. So this is what we're going to check, that they are epsilon close. So take any element of U. So we have this first inequality from the modified Walsh lemma, from the definition of epsilon bar, this is less than or equal to delta of SAU. So by continuity, this implies that if we apply P to S prime U and P to SAU, this distance must be less than epsilon P SAU. But remember that S is a strict section, local section of P, so in actual fact, we have this formula. The distance between P S prime U and AU is less than epsilon AU. On the other side, again, by modified Walsh lemma, we have this distance is less than this number, which turns out to be less than or equal to epsilon PSAU, which is epsilon AU. So notice that these two inequalities are saying that these two elements, PS prime U and U, belong to this ball. So this is the condition for S prime P and inclusion to be epsilon close, and therefore they are homotopic. So this is S prime is a local homotopy section of P, and we are done. This is the proof, or at least the sketch of the proof for this result. Recall again the result. Well, we have proof is this. Again, any vibration with A and B, E and B, ANRs, and then we have this equality. So as a consequence, we have this result already given by Srinivasan. If a space has the homotopy type of a connected CW complex, then the category of X is the generalized category of X. Here, just to take into account that both the category and the generalized category are homotopy invariants, and as X has the homotopy type of path connected ANR, then we can suppose that X is actually an ANR. So just apply the theorem above to the path vibration and we conclude the result. And we have this another interesting result for topological complexity. if a space has the homotopy type of a CW complex, then the TC of X is the TCG of X. So it has a similar proof because, okay, the TC and TCG are again homotopy invariants. And we can suppose that X is ANR. We apply the result to this vibration and we are done. Another nice result is that for the expression or of the topological complexity in order to get a motion planning algorithm, that we can suppose that the cover by arbitrary sets are pairwise disjoint. This is not very difficult to check because from one cover, arbitrary cover, one can find another cover where the new subsets are satisfied that are pairwise disjoint, and each of them is contained in one of the former covers. So one can actually suppose that the cover is a partition of the space of the X cross X. Well, now I would like to talk about the monoidal topological complexity, which is a slight different situation. Now we have that the following situation not desirable for local motion, a concrete local motion planning algorithm. Here we have this funny picture where we have 2 points that are very close, but the output path is not optimal, you know? So we don't want this. So in order to avoid that situation, we require the output path from one point to the same point to be the static path. No movement from A to A. So in order to study this, okay, this is because by continuity is one point is close to the other, then the output path must be close to the constant path. This is because of what I was trying to explain. So Iwasa and Sakai, the early, at the beginning of this century, introduced the monoidal topological complexity of a space, denoted TCM, as the smallest n, such that this product admits a cover by n+1 open subsets, on each of which there exists a 3 local section, and moreover, each of them contains a diagonal map, and the output path for points in the diagonal map are the corresponding constant path. This is not a sectional category anymore. This is a different situation. We don't know much about this new notion. There is a conjecture by Iwasa and Sakai establishing that when X is a locally finite simplicial complex, we have the equality between the two of them. They are quite close. In actual fact, there is some relation. TCM is at most 1 unit from TC. And this is also an upper bound of TC. But we don't know whether these are the same invariant or not. Okay, there are some sufficient conditions that were given by Dranisnikov involving the connectivity of the space, the dimension, and the knowledge of the topological complexity for which these two invariants are the same. But in general, for this kind of spaces, we don't know so far whether these two are the same. So it is still an open problem. One of the problems of monoidal topological complexity is that it is not a homotopy invariant. For instance, take this subspace of the two-dimensional Euclidean space. This is the union of segments from n0 to infinity, where for n greater than or equal to 1, we have Ln, this is the segment joining the origin to 1/nth, and we add the kind of the limit segment. This is the segment joining 0, 0 to 1, 0. This is the space. Now this is the first segment joining 0, 0 to 1, 1, 0, 0 with 1, 1/2, and so on. And we add this last segment 0, 0 to 1, 0. Okay, this is a contractible space. For example, it's star convex through the point 0, 0, so it is a contractible space. However, the monoidal topological complexity is not 0. Here I have an argument proving this. Suppose that it's 0. I consider this global continuous section of the path vibration, satisfying that for elements in the diagonal map, we have the constant path. Okay? So then we can take this sequence of points. These are the points on the right hand of the segments, 1, 1n, and this point is the right hand extreme of the final segment. Okay, and obviously this sequence or pair of points converge to this point in the diagonal. So by continuity, if we apply S, this sequence of paths must converge to the constant path. Okay, so let me explain with picture. This is impossible, right? And this is because, okay, this is the first path of the sequence. We have here, okay, maybe the shortest trace of this path, because it has to pass through the origin. This is the only possibility. For the second path of the sequence, the same, has to pass through the origin, and so on. For the third, for the fourth. So all these paths in the sequence have in common that they have to pass through the origin, so the trace contains this segment from 0, 0 to 1, 0. For all of them, this sequence of paths cannot converge to the constant path at 1, 0. So that's it. We have that it is not a homotopy invariant. One can tell that then we have a counterexample that the topological complexity is not the monoidal topological complexity, because this space is contractible. So TC is 0, but TCM is not 0. But this is not the case, because this space is not good. This is not a locally finite simplicial complex. So, well, it is not a homotopy invariant. However, we have this result that when X is locally key connected, the monoidal topological complexity is the relative category of delta X. I will explain later. This is a homotopy invariant. It was defined by Doeruene-El Haouari. And so therefore, TCM is a homotopy invariant when we restrict to locally key connected spaces. Recall that a locally key connected space is nothing else than a space in which the diagonal map is a configuration. Examples are given by CW complexes and ANR spaces, for example. Okay? So this is not very restrictive at all. So let me explain a little bit what RelCat is. this is, we have to construct for any n, the nth Ghanaian map of any map, f, or from A to X. This is given inductively, starting at f, the map, the original map, and if the n-1 is constructed, then we take the joint construction with f. So we take first the homotopy pullback of these two maps, and from the new arrows, we take the homotopy pushout, and we obtain this Ghanaian space. And from the weak universal property of homotopy pushout, we obtain this co-whisker map. This is this dotted arrow, Gn, making commutative all the triangles that form. We have another element, this alpha n, which is kind of a canonical map from A to GNF. So the notion of relative category of F, I would say relative sectional category, because it's a bit, it can be some misunderstandings with other relative category. This is quite different. This is the smallest n such that the nth Ghanaian map admits a homotopy section, sigma, such that the composite with F is homotopic with this alpha. This is an upper bound of a sectional category, because sectional category can be also described by using homotopy sections of the Ghanaian map. But the problem for our work is that this is defined by using only arrows, not covers. So this is one of the problems that can be solved using this kind of subsets for cofigurations. So we use only cofigurations on A to X, and we say that a subset U is relatively sectional if it contains the subspace A, and there exists a homotopy of pairs, as shown here in this slide, satisfying this condition. From 0 is X, the inclusion, and h of x1 belongs to A for any point in U. So with this in mind, it is proved that if we have a configuration where the codomain of this configuration is a normal space, then the relative category can be characterized by relatively sectional open subsets. So it's the smallest n satisfying that X admits a cover by n+1 relatively sectional open subsets. So adapting this proposition, considering arbitrary subsets, we obtain the notion of generalized relative category. So considering covers by relatively sectional subsets, not necessarily open. So this is a homotopy invariant in this sense. If two configurations are connected by homotopy equivalencies, then the generalized relative category are the same. And this is the other result. If we have a configuration between ANRS, then the relative category and the generalized relative category are the same. So this is a sketch of the proof, not the roof, the proof. And we consider just a factorization of the configuration through a homotopy equivalence followed by a fibration, and where this space in the middle is a ANR. This is not very difficult to check. And then one just has to consider a similar proof to the one given for the sectional category, and everything goes well. So As a consequence, we have that the monoidal topological complexity of X, if X is ANR, then it's the generalized topological monoidal topological complexity of X. Just as any ANR space is locally connected, we have this result already given. The TCM is the red cut of the diagonal map. And just proving this inequality, which is not very difficult to fulfill, then we have that the monoidal topological complexity is a lower bound of the generalized monoidal topological complexity. So we have this inequality. The other inequality is obvious, so we have the equality. That's all. Thank you very much for your attention.
Thank you, Jose.
Mm-hmm.
If there are any questions, please bring them forward now.
I have a question. Well, it is really a comment. For instance, in the argument for when you prove that the generalized sectional category of a vibration agrees with the standard sectional category, this concept of epsilon closeness seems to be central.
Yeah.
Okay, so I was wondering if you think of the corresponding situation in terms of the simplicial sectional category, homotopy distance in terms of previous talk of Kike. It would seem to me that some things might be doable, but replacing this notion of closeness by the notion of what is it, the name? Being contiguous. If you are dealing with simplicial maps, you can consider maps that are contiguous in the sense that if they are defined in simplicial complexes, and if you look at their evaluation at that simplex, then they have to be sent into different simplexes probably, but they are to be inside a larger simplex. So this is a sort of a concept of closeness in the simplicial sense. So I was wondering whether there could be some sort of relation describing a generalized version of simplicial topological complexity of simplicial sectional category or something like that.
Mm-hmm.
Homotopy distance.
I don't know, Jesus. I haven't thought about this. What should be a notion of generalized simplicial sectional category of X by using what? Covers by arbitrary, I don't know.
Well, what I had in mind is actually TC. And when you look at TC, you're actually comparing the two projections restricted to open sets, and they have to be a homotopic. So now you can approach this in the simplicial sense by taking simplicial approximations and replacing the concept of being homotopic by being of contiguous, by a chain of maps that are pairwise contiguous in the sense that I said. So, well, perhaps it's not very well posed, this question, but I was just wondering of the closeness between the epsilon closeness concept that you use in your proof.
Yes, and also this is very important, but also at least for my proof, the modified Walsh lemma is also very powerful and it's widely used. So I don't know. I have to check. Maybe there are some things that can be done, but I don't know honestly whether it is you can pass from continuous to simplicial. But you don't know.
Thank you.
Okay.
I have another question about the generalized TC2. About the Walsh lemma. I was wondering if this gives you like an explicit way to construct the section. So in particular, if you have an algorithm for the robots to move in arbitrary sets, does this give you a way to actually extend this algorithm? I mean, a concrete way to do the extension of the algorithm to the open sets?
I don't think so. I don't think so. These are just a question very theoretically. So maybe if you go deeply into the proof, maybe you can find a way to enlarge. But I don't think it gives you a particular way to construct local motion plannings. I don't think so. But I don't know, maybe trying to study a little bit more. But my feeling is that this is just in theory. This is very theoretically.
Okay, thank you.
Further questions or comments?
Can I might have a question. By the way, I think this is a very nice foundational result, and it's a shame we didn't arrive at it sooner. But so you say in the theorem, you said if it's a fibration, then the generalized sectional category is equal to the sectional category.
Yeah.
But if you have like a map, you can define the sectional category of a map by either turning it into a fibration first, and then by the homotopy invariance you mentioned, you'd get a well-defined thing, or I think just by taking local homotopy sections.
Yes.
So does the theorem apply there also for an arbitrary?
I wanted to the statement of the result is that we have a fibration between ANRs. But I had problems if we started with just a map between ANRs, because I need from the very beginning, I need the local section to be strictly local sections. If not, then everything's screwed up. So at least from my proof. So you say, for example, if you have a map between ANRs, then the sectional category and its generalized version are the same. I'm not sure. At least using my proof, I can find a lot of problems because of that, because I need at the very beginning of the proof to start from local strict sections. I don't know if I answered your question.
Okay, but it so happens that if X is an ANR, then the free path space and the based path space are known to be ANRs. So
yes, because there is a path, because the topological complexity and the generalized topological complexity are homotopy invariants. So I can avoid that problem, because if a space has the homotopy type of an ANR, then as they are homotopy invariants, we can suppose that from the very beginning, the space is ANR. And we can go on, and we can use the theorem. But not by using a general result stating that we have a map between ANRs, then the sectional category and the generalized sectional category agree. It's kind of tricky. Yeah.
Okay, thanks.
You're welcome.
I have also a question. First of all, I mean, it's really a nice result and very useful, as Mark said. It's pity we didn't have it earlier. That's right. There was something similar in a paper of Pavesic. So maybe you can comment on distinctions on the, between your result and his result. And secondly, I mean, the second question is a little bit, I don't know, not very precise, but I thought that maybe it is possible to have this partition and the sets such that their dimension is decreasing, such that there are no two sets having the same dimension, kind of. I mean, make further step and kind of require that this set, this partition sets have some kind of decreasing dimension. Maybe it is a bit vague, but I feel that it could be possible, but I don't know. So if you don't want, just answer the first question.
I don't know. I haven't thought about your second question. I haven't thought about it really. So I just get into just a partition of the product X across X. But maybe it would be interesting that I didn't have that feeling. So you think that maybe the subsets have decreasing dimensions, something
Yes.
like that?
Yeah, I can explain why. Well, I mean, suppose you're looking at, let's say, sphere bundle, and you take this vector bundle, and you construct a section of vector bundle. So it has, vector bundle always has a section. So there is some zero set. And this zero set you throw out. So on the open set, you have section of the sphere bundle. And then so you have zero set of smaller dimension. And even you can say this codimension something. And then on this, you will construct another section and so on. So kind of inductive. But it maybe this intuitive kind of picture applies only in certain cases. I don't know.
Okay. And about the first question, you're right. There is a paper by John Oprea, I think. Maybe John can say something.
No, it was a draft we did with Michael and his student, Lewis Mead.
Ah, sorry. By you, sorry. I have to admit that I haven't read that paper, but I think that...
I'm asking about paper of Pavesic. I think there was something.
Pavesic.
Pavesic, yes. He published something, no?
I don't know.
Maybe.
Well, Michael, I think he proved something similar, but they had to be compact ANRs.
Something like that, yeah.
Yeah, and that's maybe too restrictive for having,
yeah,
you know, something. So I think that's what I remember.
Yeah, okay.
Yes, and I have to also to say that okay, there is a paper by you and your student, no, that it faces this problem of the generalized sectional category, and it has more results about this, right?
No.
No,
I don't think so.
Well, Michael, I sent the write-up we had to Jose.
Oh, it was something internal. It was not a paper.
It's not a paper. No, Jose, I told you that.
Okay, this seems like a good place for me to pause the recording.